Hi, in this video, I'll be solving this problem. It's a very typical flow-in, flow-out problem in a calculus class, and this particular question is from the Stewart Calculus book. Let's read this problem and draw a diagram at the same time. A tank with a capacity of 400 liters is full of a mixture of water and chlorine with a concentration of so much. So we have a tank of liquid. With that concentration of chlorine. In order to reduce the concentration of chlorine, fresh water is pumped into a tank at a rate of 4 liters per second. So you have incoming pure water at 4 liters per second, and the mixture is kept stirred and it's pumped out at a rate of 10 liters per second. So it's getting pumped out at 10 liters per second. The incoming water is just pure water, and the mixture coming out is the well mixed with chlorine in it. Find the amount of chlorine in the tank as a function of time. Okay, so first let's strategize. Let's say that y of t is the amount I want, is the amount of chlorine in the tank. Then it starts out at 400 times 0.05. So it's 20. And then it changes over time. It changes over time because pure water is coming in. So there's 0 gram per liters coming in, but there's some non-zero chlorine out. So overall, it'll change over time. So for things that change over time, I need that quantity. Then the knee-jerk reaction is to find the rate of change and work backward from there, right? So I need the rate of change of y with respect to t. And as a matter of fact, I know what the rate of change is because I know that this is the rate of change. This is how much chlorine I lose over time. How much chlorine I lose per unit of time is 10 liters per second times whatever the concentration. The concentration started at 0.05 grams per liter, but it doesn't stay 0.05 because water, fresh water is pumping in, so it dilutes the chlorine all the time. That means I will need to know the concentration. And concentration is equal to amount of chlorine divided by the total amount of liquid. That's the definition of concentration, right? So now I know my strategy. In order to find the total amount of chlorine, I need to find the rate of change of the chlorine. And in order to get the rate of change of chlorine, I need to know the concentration of chlorine. But concentration is defined as amount of chlorine divided by total amount of liquid. So that means before that, I need to find the amount of liquid. Those are the steps I know I'm going to need. So I'm going to work backward. And the first thing I'm going to do is to compute the total amount of liquid as a function of time. From that total amount, I can calculate the concentration as a function of time. From that, I can calculate the rate of change. And then from there, finally, I get to the amount of chlorine as a function of time. So those are my 4 steps. In addition, because I know that I'm going to get very confused with amount of chlorine, concentration of chlorine, amount of liquid, rate of change, all of those things. And so for all of these calculus and differential equations that involve multiple quantities, my advice is to keep track of the units. When you keep track of the units, you can double check on all your calculations to see if at least they make sense. Do they at least make sense? Okay, keeping all that in mind, we're ready to get started. First, we define our variables. Let y of t be the thing they're looking for, which is the amount of chlorine as a function of time. And the amount of chlorine is measured in grams. And the time t is in seconds. So according to our strategy, the first thing we're going to calculate is the total amount of liquid. Well, the total amount of liquid started with 400 liters. And then 4 come in and 10 comes out. So for any given time, we gain 4 and lose 10 for a net of -6. So the amount of liquid in the tank at time t is 400 minus 6t. Now let's check the units. The 400 is in liters. The 4 and the 10, the 4 coming in and the 10 coming out, are in liters per second. And the time t is in seconds. So what I have is L plus L over S times S like this, and the seconds cancel. Liters plus liter is liter. So that makes sense. The amount of liquid should be in liters. That works. The second step is to find the concentration of chlorine. This is actually the step that a lot of people get stuck on. But it turns out to be a lot simpler than you think. Because concentration of chlorine is defined by how many grams of chlorine per liter, right? So that means you want total amount of chlorine divided by total liquid. Well, it turns out that we do know what the total liquid is. That's 400 minus 6t. And we also know what total chlorine is. I mean, we don't really know, but we have a symbol for it. There it is. The total amount of chlorine is Y. So we don't know what Y is, but we have a symbol for it. It's Y. Y over 400 minus 6t. Let's check the units. What's Y? Y is the amount of chlorine and is in grams. So this is grams. And 400 minus 6t, we checked last time and we knew that it's in liters. So all of this is grams over liter. Gram per liter, that is the correct unit for concentration. And if you are unsure, you look back at the statement of the question itself, and it says right here, the concentration is in grams per liter. So grams per liter is the correct unit. Step 3, we're going to find the rate of change of the chlorine, which is the rate of change of Y, basically. For these like flow in, flow out problems, and as you go on in your career, you may find more complicated problems like go in to one bucket, goes out and goes into a second bucket, and it goes into a third bucket, etc., etc. But all of them are pretty simple. The net rate of change, all of them, no matter how complicated they make things, boil down to just this principle. And that is that the net rate of change is the rate coming in minus the rate coming out. In this case, the rate coming in is 4 liters per second, and the rate going out is 10 liters per second. But if you think about just the chlorine, then there's 0 chlorine here because it's pure water. This one has chlorine. And therefore, the rate coming in is 0. And the rate going out is 10 liters per second. But it's not all chlorine, right? Only some of it is chlorine. And how much of it is chlorine? This much of it, that concentration of chlorine times the concentration. And we have the concentration on step 2. So this is 0 minus 10 times Y over 400 minus 60. Now let's check units again. Unit of the Y is gram. Unit of this is liter. We check that in step 2. And what's the unit of 10? 10 is the flow of water, so it's 10 liters per second. So the unit here is liters per second. And so if you put them all together, it's liter per second times grams per liter. The L's cancel. I have G over S, grams per second. Is that the rate of change of chlorine? Yes, chlorine is measured in grams, so the rate of change of chlorine is grams per unit time, per second. So that also makes sense. All right, so this is the rate of change of chlorine. Chlorine is Y, so the rate of change of chlorine is dy dt. Therefore, I have my rate of change dy dt is equal to negative 10y over 400 minus 6t, like that. Once I have this, I can find the amount of chlorine, Y, by basically solving this equation. All right, I look at this and I recognize that it's a separable equation. It's separable because I can multiply and divide things in such a way that all the y's on one side times dy and all the t's on the other side times dt. Specifically, if I divide by y, then you'll go over there. And if I multiply by dt, then dt will go over there. Like this. I divide both sides by y. Then these y's cancel. I multiply both sides by dt. Then these dt cancel. My equation becomes it is now separable, so I can integrate both sides. And on the left, I have ln of y. And on the right, I do a u substitution where u is equal to 400 minus 6t. du is negative 6 dt. So I'm going to rewrite like this. I'm going to put the negative 10 on the outside. I multiply by negative 6 and divide by negative 6. I arrive at 5/3 integral of du over u, which is equal to 5/3 ln of u plus c. And I substitute back 5/3 ln of 400 minus 60 plus c. Like that. Until the tank is empty, then first of all, the total quantity of liquid is going to be positive. And the amount of chlorine is also going to be positive. And so I don't need the absolute values. So I can write ln of y is equal to, and then for, I know eventually I'm going to need to take e to the power both sides. So I want the ln to stand by itself. So I'm going to use the property of ln and bring that 5/3 power over there. And like I said, I don't need the absolute value anymore. So it's going to be just 400 minus 60 to the 5/3, like this, plus c. Now I can take e to the power both sides. So the e to the power ln cancel. I have y on this side. I have and times e to the c. C is an arbitrary constant. E to the power c is just another arbitrary constant. So I can replace the whole thing with a factor of a. So that's my y as a function of t. I need to figure out what a is. And the way to do that is to use the initial value. I'm not really given the initial value in the problem, but I am given enough information to find it, because y is the quantity of chlorine. Well, quantity of chlorine is total amount of liquid times the concentration. And I do know what both of them are at the beginning. At the beginning, the total amount of liquid is 400 and the concentration is 0.05. So I do know what it is at the beginning. It's 400 times 0.05 and it is equals to 20. Well, let's check units. 400 is liters. And 0.05 is grams per liter. So when I multiply like that, the L's cancel and I have just grams. So that works, it's 20 grams. So I plug into that equation, I let t equal 0, then have y of 0 is equal to a. Y of 0 is 20. 6 times 0 is 0, so it's a times 400 to the 5/3. I don't know what 400 to 5/3 is. I'm just going to leave it like that. So I have a, I plug back into that solution. That's a perfectly legit solution. Now, those of us who are a little OCD, we may care to simplify this because I noticed that there's a 400 to the 5/3 here, and there's a 400 inside of here that's also raised to the power of 5/3. So I know they could be canceled. So you can leave your solution like this, but I'm a little OCD, so I'm going to try to clean this up. I'm going to factor a 400 out of this. So I have 1 minus 6 over 400 t like this. And then the whole thing is raised to the power 5/3. And that means I can separate out a 400 to the 5/3 separate from this. And then if I multiply by 20 over 400 to the 5/3 in front, then these cancel. So an alternative form of the solution is y of t is equal to 20 times and like this. And like I said, those of us who are OCD, we kind of like this form of the solution better. First of all, because the 5/3 doesn't appear too many times. It doesn't appear in the denominator. But a better reason still is that when you look at this, it's very clear that the initial value is equal to 20. When you plug in t equals 0, this whole thing goes away. And you just have 1 to the power something. Well, 1 to the power something is just 1. And so the initial value is just 20. Having the initial value appear by itself in front is very desirable to a lot of people because they're used to expressions like a e to the kt kind of expression, right? Where the initial value appears in front like that. So yeah, this alternative form of the solution is preferred by a lot of people. But like I said, the first form is perfectly legit. If there's nothing wrong with it, you can perfectly leave it like that. All right. Hope that helps. Any questions or comments? Put in the comment section below. For a lot of these differential equations, it's a good idea to double check the units. Like, share, and subscribe for more contents. Thanks for watching. Bye.